my clock says 1:59, so I have the luxury of some one minute more of opening remarks. so, uh, so anyway, of course, thank you very much to the organizers for allowing me to be a part of this of the Balu Fest. I have been also lucky to be there on previous such celebratory occasions. But I'm happy that the one new thing this time is that I can now call myself a collaborator of Balu, and also a former colleague since he was at IIT Bombay for 3 years. So that's new, I guess. So I will kind of um, apologize because at least some parts of this talk I have given before. It's not identical to a talk I gave about 6 or 7 months ago. There have been some new results since then, so those will be incorporated. On the other hand, I would say that the first 20 minutes of the talk are really propaganda, and of course, propaganda works best when repeated. So maybe that's not such a bad thing. Okay, so let me just begin with a very elementary thing. Just let me set things up a bit. So, sorry. Maybe just I should say mute all for the moment and allow participants to unmute themselves. Okay. Okay. So the title of my talk is on Dirichlet series of degree d greater than or equal to 1 in the class A sharp. This is Gothic A, and that sharp is something that seems to have entered the literature in many contexts. So I will retain it as well. So let me explain what this class A sharp is. So, okay. All right. So let me start with a very classical theorem due to Hamburger, right? And it was proved in 1921. There were a series of 3 papers. I will just give the one elementary result. And so the starting point is a Dirichlet series. And one assumes that ds converges in some right half plane, real is greater than sigma a. Actually, Hamburger took sigma a to be 1. So he assumed that the half plane of absolute convergence of the Dirichlet series was 1. He also assumed that essentially ds had an analytic continuation to the whole plane. Not quite. It has an analytic continuation to an entire function after multiplying by some polynomial. So in other words, you're assuming that ds has a finite number of poles. It has a meromorphic continuation to all of C with at most a finite number of poles. Okay? But there is no restriction on the orders or locations of the poles. And one also has this technical assumption that seems to be something we really cannot get rid of. We assume that ps times ds is entire and is bounded in vertical strips of finite width. So this is, of course, a standard assumption. It is made so that at some crucial point in all proofs, one can use the fragment Lindelof principle. This particular condition can and will be weakened to, for example, you can allow polynomial growth or sub-exponential growth. But in any event, after the fact, once you assume polynomial growth, you will anyway come back and show that the function is actually bounded. So there is no real harm in assuming that it's bounded in vertical strips. So, okay. And finally, ds satisfies a functional equation, the standard functional equation that the Riemann Zeta function satisfies, right? Pi to the minus s by 2, gamma s by 2 ds. You call that lambda s, and lambda s is lambda 1 minus s. And in that case, Hamburger showed that ds is nothing but constant times zeta s. Okay, so this was, in some sense, the first time anybody tried to characterize Dirichlet series in terms of their analytic properties. Perhaps one should say in terms of their analytic and geometric properties, because the functional equation is usually viewed as a manifestation of a geometric property. So the real question is, to what extent do the analytic properties of a Dirichlet series characterize it? And here we have a very satisfactory theorem, namely that anything, so informal way of perhaps stating Hamburger's theorem is that anything that looks and smells like the zeta function is actually the zeta function, or a constant times the zeta function. So Hamburger's theorem is an example of what has been called a converse theorem. The name converse theorem actually comes from Hecke, and that's a characterization of a Dirichlet series in terms of its analytic properties and functional equation. And in fact, he actually proved a slightly more general result for the Dirichlet series LS chi. So slightly more general than that. So in some sense, motivated by Hamburger's theorem and of course many other developments to which I'll come back a little later, I would like to ask the following question that many people have asked, right? How to characterize the properties of analytic of automorphic L functions? How to characterize, in other words, can you give a set of analytic properties that more or less characterizes the properties that automorphic L functions have? And the Riemann zeta function, of course, is the simplest example of what are called automorphic L functions. I will not define an automorphic L function because, well, first of all, it's complicated and it really serves no purpose, but we'll work through examples. But here is what I would like to do. I want to define a class of Dirichlet series. And at least conjecturally, this, that is, if one assumes various standard conjectures about automorphic L functions, this class of Dirichlet series should capture all of them. And the other thing it should do is a little stronger. Suppose it should capture all known examples of automorphic L functions, which have meromorphic continuation to all of C. So maybe actually this is slightly badly worded. In general, we do not know if I'm given an automorphic L function, I do not know in general whether it has a meromorphic continuation to all of C with at most a finite number of poles, right? But suppose I do know that, then I should be able to state with confidence that it lies in my class of Dirichlet series, right? And there should be no conjecturally. So if I have an example, if I know that an automorphic L function has at most a finite number of poles on the whole complex plane, then I should be able to say that, oh, it's in my class of Dirichlet series. And finally, I want this class of Dirichlet series small enough that again, conjecturally, all its elements are actually only linear combinations of automorphic L functions, that we don't really get much more. So linear, one can ask what linear means. Okay. Technically, maybe I need to allow coefficients in which are themselves finite Dirichlet series. Okay, so but we won't need to think about that too much. So essentially, I want a class large enough to contain all known examples, but small enough that the known examples are essentially the only ones. And we would like to actually prove some theorems. Obviously, if you make the class too general or too large, it will be difficult to establish any kind of a theorem. On the contrary, if the class is too small, which I believe is a problem with some of the existing classes, other than then one is excluding a lot of known examples. So let me just very briefly remind you of some known examples, essentially maybe for some of the students who are attending. So I'm going to define the class A sharp. So this is Gothic A, and that's sharp. So A is supposed to be for automorphic. Automorphic L functions are really the L functions that are going to provide all the examples in this class. Right? Okay. So I start with a non-zero meromorphic function on C. And I consider the following conditions on the function f of s. So first I assume that it's given by a Dirichlet series f of s with abscissa of absolute convergence sigma a greater than or equal to half. So I'm just assuming that some abscissa of absolute convergence which is greater than or equal to half. Obviously, half is not important, as we will see in just a minute. I will assume the same condition as I assumed in Hamburger's theorem, that there is some polynomial, so that after you multiply by that polynomial, p of s, the product p of s fs extends to an entire function, let's say with finite growth in any vertical strip, sigma 1 less than or equal to real s, less than or equal to sigma 2. So in vertical strips, we have finite growth. And the third one, again, familiar from the Zeta function and Hamburger's theorem, is that there is a functional equation. Okay, so this, as you can see, is somewhat complicated. So I will come back to this several times. But if you look at the final form of the functional equation, it looks like essentially some gamma functions times f of s, the Dirichlet series, sometimes some number q to the s. That if I call capital phi s, then that should just be omega times phi of 1 minus s bar. This is complex conjugation, and then you take the bar of the whole thing. Okay. In terms of Dirichlet series, it just means that on the right hand side, I will have the Dirichlet series summation an bar by n to the s. Okay. So we will have to look more closely at these functions g of s. Okay. So let's look at the structure. I'm allowing a certain number of gamma functions in the numerator of the form gamma lambda js plus mu j. J equals 1 through r. I'm also allowing some gamma functions in the denominator. So I can also divide by gamma lambda j prime, prime s plus mu j prime, and so on. Okay, so this is, as you can see, more complicated. Just let's remind people of what this is in a number of concrete examples. So that's next. Okay. So in all of the examples below, sigma a is going to be, sorry, my apologies, that's not 1. It should be less than or equal to 1. Sigma a is less than or equal to 1, and ps equals s minus 1 to the m, and m will be either 0 or 1. So ps is actually going to be either 1 or just s minus 1. Okay. So this is the polynomial. So in other words, the Dirichlet series is going to have at most a simple pole at s equals 1. And it will have abscissa of absolute convergence less than or equal to 1. Okay, so we started with the Riemann zeta function, and I'm just telling you what the GS is in each case. So in this case, so remember, GS is the thing that you put in front of fs, bunch of gamma functions, and I'm telling you exactly what the GS is in a bunch of examples. So for the zeta function, of course, g of s is just gamma s by 2. So in that case, the number of factors, gamma functions that occur in GS in the numerator is just 1. For that particular gamma factor, lambda 1 will just be half, that's s by 2, the coefficient of s. Mu 1 is actually 0. There are no gamma functions in the denominator in the functional equation. And if I take twice the sum of the lambda j's, and there's just one lambda j, namely lambda 1, then I get 1. Okay, so I'm going to look at these numbers for 3 or 4 examples. So for the zeta function, this is what we get. We have the Dirichlet L functions. It's very similar, where ls chi, where chi is a primitive Dirichlet character. Again, there will be only one gamma function occurring, and it will occur in the numerator, right? It's given by this formula, chi minus 1 equals minus 1 to the epsilon, and epsilon will be either 0 or 1, according to whether chi is even or odd. And again, r is 1, that is the number of gamma functions in the numerator that occur in the functional equation. Lambda 1 equals half. Mu 1, of course, now is epsilon by 2, maybe the 0 or half in my notation. R prime, the number of gamma functions in the denominator is 0. And once again, twice the sum of the lambda g's is 1. So there's no real change in this. Okay. So notice that in particular, mu 1 is either 0 or half. So its real part is greater than or equal to 0. So this becomes relevant in the next one. So suppose I have a unitary Hecke character of some number field, k over q, and degree of k over q is n. Now here, you will typically have n gamma functions occurring all in the numerator, this n being the same as the degree of k over q. Right? And in every case, all the lambda j's, that is the coefficient of s, is again a half. Okay. One can describe the mu j's more precisely, but what I will just content myself with is saying that the real part of the mu j's will be greater than or equal to 0 in all of these cases. Okay. There will be n such factors in the numerator, no factors in the denominator, and the twice the sum of the lambda j's will be exactly n. So this is, and example 4. So 2 more examples. If I have a holomorphic form of weight k greater than or equal to 1 and level n greater than or equal to 1, then again, you have G of S, then you can think of as being one factor. You could also, by the way, think of it as being two factors using the duplication formula for the gamma function. But anyway, we will write GS like this, then R equals 1, lambda 1 equals 1. In this case, the coefficient of S, mu1 is obviously k minus 1 by 2, which is greater than or equal to 0 because weight of k is bigger than or equal to 1. R prime, number of factors occurring in the functional equation, is 0 in the denominator. And twice lambda, sum of the lambda j's is 2. Okay? So in the previous examples, twice sum of the lambda j's was 1, now it's 2. And another perhaps example, you take the symmetric power L functions, right? Never mind what they are, but roughly for n equals 2, the coefficient of the symmetric square L function is just a sub n square of the coefficient of f, where f is a holomorphic modular form. And in that case, once again, you have some number of gamma functions in your numerator. How many? Exactly n plus 1. Right? Again, the lambda j's are half, the real mu j's are greater or equal to 0. R prime is 0. So in all our examples, of course, R prime has been 0. And twice the sum of the lambda j's is n plus 1. Okay. So these are the possibilities. And finally, we can also look at mass forms of level n, and we have a similar description. Again, in that case, okay, R equals 2. Only gamma functions appear only in the numerator. Lambda 1 equals half, lambda 2 equals half, and the real part of mu j again will be greater than or equal to 0. I've chosen a mass form of level n equals 1. That's important, as we will see. R prime, number of factors in the denominator is 0, and twice the sum of the lambda j's is 2. Okay, so this should be familiar. All right. So why did I give all these examples? So we have defined a class called A sharp. But of course, this didn't come out of a vacuum, right? Famously, Selberg defined the Selberg class S, and Kaczorowski and Pirelli defined the extended Selberg class S sharp of the Dirichlet series. And I'm going to compare the series A sharp that I defined with S sharp. What is the difference? Okay, a non-zero meromorphic function Fs is in the class S sharp if it satisfies not P1, but P1 prime. What is P1 prime? So P1 was some abscissa of absolute convergence. We didn't specify what sigma A was, as long as it was bigger than or equal to half. But for S sharp, one specifies that sigma A is less than or equal to 1. So that's the one key difference. A sharp has no restrictions on the half plane of absolute convergence, but S sharp, the extended Selberg class, you demand that sigma A is less than or equal to 1. So that's obviously a significant restriction. Likewise, P2 prime is stronger for the Selberg class. You can't take any polynomial you like. You can only take the polynomial s minus 1 to the m for some m. So in other words, you're assuming that your Dirichlet series has meromorphic continuation to the whole complex plane with at most one pole. If m is 0, in fact, you assume you're making the assumption that it's entire, but the only pole you're allowing for the Dirichlet series is at s equals 1. So again, obviously, it's a much stronger condition. And P3 prime. So what is P3 prime? It's again stronger than P3, right? First, in the Selberg class, one does not allow gamma functions in the denominator in the functional equation. And secondly, we always assume that real mu j is greater or equal to 0, which again was not an assumption in A sharp. A sharp had no conditions on the mu j at all. So you can see that each of the three conditions, P1, P2, P3, right, is weaker than the corresponding conditions imposed on the extended Selberg class. And now I'll explain why one actually weakens this. So all the examples that we saw so far all belong to the extended Selberg class S sharp. Okay. And of course, therefore to A sharp, since A sharp is a larger class. So two things. Very often, we are given an L function, even when we know or expect that an L function satisfies P2 prime, that is the stronger condition, that is that it has a pole only at s equals 1, right? It is usually not something that is easily proved, right? Meromorphic function with a finite number of meromorphy with a finite number of poles on all of C is typically not so hard to establish, not so easy, right? But not so hard. So P2 is not too hard to establish. There are standard methods called the Langland-Shahidi method, etc., which do this. But determining the exact location of the poles and saying that there are no poles other than at S equals 1, that is much harder. Okay. Sometimes one cannot do it, and I mean, one expects maybe that one can do it, and one simply cannot do it. But even when one can do it, it's usually a lot of hard work. Yeah, people work very hard to prove this. And this will come back to establishing P3 prime, that is, especially this real mu j greater than or equal to 0, is equivalent to establishing what is called the generalized Ramanujan conjecture at infinity, which is again a major conjecture and on which there is very, very little progress. So, all right. So let me first give some more examples which will highlight the contrast between S sharp and A sharp. Maybe this is a good time to just pause for a minute and ask if there are any questions. Perhaps I'm responsible for, I've been made the host, so I should check if there are any raised hands, I guess, or something. Appears not to be the case. Okay. So, all right, great. Okay. So, what we have said so far is, look, there's this class A sharp, which is bigger than the extended Selberg class, and we have noted the differences. Let me give you some examples to highlight the differences. So as I was saying, very few, in fact, you'll see that very few of the functions in A sharp are even conjecturally expected to belong to S sharp, and even fewer are actually known to belong to S sharp. And essentially the only examples that we know in the extended Selberg class are those examples we have discussed so far. We can build a few more. For instance, we can take the symmetric second, third, and fourth powers of mass forms, and we will again get L functions in the extended Selberg class. But that's pretty much it. I mean, you can maybe some Hilbert modular forms, one or two in a few cases, but really almost everything is already accounted for by what I have given. Okay, so here are some examples which are only conjecturally in the extended Selberg class. That is, we know they are in A sharp, but we are not sure, we have not yet been able to prove that they are in the extended Selberg class. So one is, suppose you have a mass form of level n greater than 1, right? In general, then you cannot show that it's in the extended Selberg class because its gamma functions look like this, some gamma s plus mu 1 by 2 and gamma s minus mu 1 by 2. But the problem is that you cannot prove that real mu j is greater than or equal to 0 in general. Okay, this is in fact what is called the this is the Selberg eigenvalue conjecture. So obviously it's a very deep conjecture, has remained unsolved. It is known for small values of capital N. So I think maybe up to 9 or 10, I'm not exactly sure, but certainly for n equals 1, it's known, and for certain small values. But for a general congruent subgroup, this conjecture is not known. So here's an example. But since A sharp does not require any constraint on the mu j's, we know it belongs to. So even the L functions of mass forms of higher level are not known to lie in the extended Selberg class. Here's a more complicated one. So what pi is what's called a cuspidal automorphic representation of GLNAF, whatever these things may be. Then every time you have such an object, you get an L function ls pi, and its L functions will have a functional equation, etc. And you can see that there are m times n gamma functions occurring in the numerator, where m is the degree of f over q and n is the n of gln. So you can construct higher degree L functions as they're called. So what is the degree? Really, it is this twice some lambda j, which previously was either 1 or 2 in all my examples, is now m times n. Okay. So these functions are known to be in A sharp. So we know that they have a meromorphic continuation, a functional with a finite number of poles. We know they have a functional equation with this GS. What we don't know is the generalized Ramanujan conjecture, and that would tell you essentially that real mu j is greater than or equal to 0. So, the very special case f equals q and n equals 2 itself is not known. That is the Selberg eigenvalue conjecture. So of course, this very general conjecture is very, very far from being known, I don't think people have any idea how to attack such a question in general. There are other functions associated with these cuspidal automorphic representations. They will all give, you know, twice the summation of the lambda j's in these cases will all be large integers, right? So if pi1, if I have pi1 and pi2 as above cuspidal automorphic representations on n1 and n2, then, you know, this twice summation lambda j will be n1 times n2. So there are other objects. So symmetric square of pi, this is like symmetric square of f that we saw before. There's something called the exterior square L function. These are all relatively well understood. We know they belong to A sharp, but we have no idea whether they belong to S sharp. Well, we believe they belong to S sharp, but the generalized Ramanujan conjecture is the obstacle. Right? So first of all, we have all these L functions. We have all the nice properties for them except GRC essentially. So we know they lie in A sharp, but unfortunately, if you prove a theorem in the extended Selberg class, it will not apply to any of these L functions. So this is one reason you would like to actually prove theorems in A sharp. And finally, here are examples which are absolutely not in the extended Selberg class, but in A sharp. So there are two. So one thing you can do is you can simply take something in Selberg class and translate it. So you can just look at LS minus alpha and LS plus alpha. So for instance, very concretely, you can take zeta S plus half, zeta S minus half times zeta S plus half. Okay, and this will violate everything. So for example, the zeta S minus half to zeta S plus half, its abscissa of absolute convergence will be 3/2. So definitely bigger than 1, right? The polynomial you need to multiply by will be S minus half and S times S minus 3/2, right? So it's more complicated. And yeah, so clearly it cannot lie in the extended Selberg class when real alpha is relatively large. If you take this kind of L function, LS minus alpha times LS plus alpha, you have elements in A sharp, but not in S sharp. So not even conjecturally is this going to work. More equally natural examples, for example, one can take the so-called non-generic representations of GL and AF. And in classical language, for example, that would be something, say, that corresponds to a Siegel modular form. So if you have a Siegel modular form, in general, you don't expect LSF to lie in the extended Selberg class, but it will lie in A sharp again. And one more thing, which is certainly of interest to many people in this audience, if you look at the half integral weight modular forms, then their L functions will not belong to S sharp, but they will belong to A sharp. So for simplest example will be zeta 2S minus half. So even that is excluded in the Selberg class because sigma A is 3/4 in this case. Okay, so less than or equal to 1, but the polynomial PS is S minus 3/4. Okay, so that's where we stand. I'll make a final pitch for R prime. Why do we allow R prime greater than 0? Because of course none of the examples I've given allow that. Okay, why do we allow, in other words, gamma functions in the denominator of our function equation? As I said, there are in fact no known, at least I know of no known examples of series for which R prime greater than 0 is necessary, right? And I would guess that if you have a functional equation where there are some gamma functions in the denominator, you can replace those functions. I mean, it will be true that the function f of s will satisfy a functional equation, some other functional equation where R prime is in fact 0. So I'm guessing one can always do this. I cannot prove it. But one thing is it allows us to treat quotients of L functions. So if you take something like Ls plus k minus 1/2f and divide by Ls chi, where f is a say modular form or mass form, right? This sort of function will have a functional equation, right, with gamma functions in the denominator. Of course, one does not expect such a function to lie in to have only a finite number of poles. So one doesn't expect this sort of function to lie in A sharp. Okay, but I don't know if any way of excluding that, except by first assuming that in fact it lies in A sharp using the methods of the stock and then ruling that out as a possibility. Okay. The other place where quotients of L functions occur naturally are Artin L functions. The Brouwer-Aramata theorem tells us that Artin L functions are quotients of LS chi's, where chi is a Hecke character for number field. So I should also add that Booker has defined another class of L functions, which he calls L. I would have liked to call my class L, but he had already taken that, and that's again an axiomatic characterization. But that's I cannot prove right now, though I strongly believe that our class contains L. Certainly, it is true that our class has lots of elements that do not belong to L, and L has very strong conditions, including mean square average Ramanujan and an Euler product and so on. So notice one of the features of our class is that there is no Euler product, which means in particular that linear combinations of elements in our class can lie in our class again, right? Okay, so I think this is certainly a much larger class than Booker's class. I cannot definitively prove, but every known example of an L function that lies in L definitely lies in A sharp, and conversely, there are lots of examples of elements in A sharp that do not lie in L. Some given by the previous examples on the previous couple of slides. Okay, so that finishes the propaganda segment, which has gone on a little longer than I intended. So let me state the results. Okay. So we came across this quantity twice summation lambda j minus twice summation lambda j prime prime. We came across this because the second term was 0 in all examples. And this quantity we call df. Okay. So these numbers are, of course, come from the function equation. And a priori, the quantity df, which, by the way, I will call the degree, seems to depend on the choice of gs that appears in the function equation. So just to remind you, this is what gs looks like. It appears in the functional equation, right? And there may be, a priori, it's not clear whether gs is unique. Indeed, it's not unique. Okay. But what is true that nonetheless, that the degree is unique. This is an invariant. It doesn't depend on the choice. So we have a theorem. This number df, which I'll call the degree, does not depend on the choice of the functional equation for f of s. And the proof of this is not hard and imitates earlier proofs for the extended Selberg class, essentially due to Conry, Ghosh, and Kaczorowski and Perelli. Okay. So this is not hard. It's a straightforward. But what this allows us to do is to, take our class A sharp and decompose it as the union of A sharp D, where D is the class of all, A sharp D is the class of all series F in A sharp, such that the degree is D. Degree of F is D. So now it reduces the problem of studying A sharp to the individual classes A sharp D. And now we can get going. So the first conjecture is a degree one would like to make is a degree conjecture, right? Which says that if D is not an integer, then A sharp D is empty. So there are no elements where the degree is not an integer, right? And indeed, all our examples certainly conform to that situation. Okay. And of course, again, this is not from the void. This conjecture was originally made for S sharp for the extended Selberg class by Kaczorowski and Perelli. But I will now give evidence that for believing that it can equally hold in our class A sharp. Okay, so let's see classification results. So the idea, next couple of slides will classify the elements in the Selberg class of small degrees. So first of all, you can take the A sharp 0, right? Those of degree 0. So then the theorem is that it consists of Dirichlet polynomials of the form summation an by n to the s, where n divides q. So there's finite Dirichlet polynomials for some integer q. So that's a theorem. Again, not surprising, because actually what we are able to show is that A sharp 0, the degree 0 elements in A sharp, are exactly the degree 0 elements in S sharp. This requires a little bit of work because, in S sharp, having a functional equation of being of degree 0 means there are essentially no gamma functions occurring in the functional equation. Whereas for us, we can have quotients of gamma functions. Sorry? Was there a question? Sorry. There is something in the chat. Oh, it's 4 a.m. It says good night. Okay. Sorry. Lost it. Okay. So for us, there is some work to do because, a Dirichlet series of degree 0 for us can have quotients of gamma functions appearing in the functional equation, and you have to rule that out. But we can, and in fact, Kaczorowski and Perelli have slightly sharper classification, a more precise classification for degree 0 elements, and that will be valid in this class as well. Okay. And we can also prove that between 0 and 1, there are no series. Not a surprise. And here, it follows, the proof follows older results. So theorem 3 actually, in some sense, requires a little more work than theorem 4. There are no series of non-integral degrees between 0 and 1. Right? So that's the theorem. And when d equals 1, of course, we would like a characterization. So here is the perhaps the strongest generalization of Hamburger's theorem so far. So suppose you have f of degree 1 in A sharp, then f is really a linear combinations of the LS chi's, right? So basically of Dirichlet L series. You should allow the L series to be translated by I times A for some real number A, okay? Because that changes nothing, that remains in the class. The coefficients can be degree 0 elements. So of course, a product of a degree 0 and a degree 1 element in this class will give you a degree 1 element. So I'm saying that every element of degree 1 essentially is a linear combination of Dirichlet characters, possibly shifted by a unitary twist, times p chi s, where p chi is an element of degree 0. Yeah, and in fact, again, there's a somewhat more precise characterization, which due to Kaczorowski-Perelli, which goes through. Okay. So again, this theorem has been proved for S and S sharp by Kaczorowski and Perelli, right? Analogs of this theorem. But a certain amount of work again is needed to pass from the class extended Selberg class to A sharp. It's not completely trivial, but in any event, what I was able to do was to give a slightly different proof based on an idea, essentially an idea of Soundararajan. I mean, Soundararajan himself gave a different proof of the theorem with a few more restrictions. But initially, I was able to prove it only for under the assumption sigma A less than or equal to 1. But recently, I've been able to remove this restriction. So you have the, sorry, I have, anyway, so I've, that's the previous theorem, right? So here I've made no assumption on the abscissa of absolute convergence, if you look at it. And that's somewhat recent. All right. The big theorem that I have, so first one, I'm happy that I can mention that this is joint work with Balu, right, which we proved a few months ago, that there are no elements between 1 and 2. There are no elements in this A sharp between of degrees between 1 and 2. So this is further evidence towards the degree conjecture in A sharp, right? So we have nothing between 0 and 1. We can classify the elements of degree 1. If you like, it's a jazzed up version of Hamburger's theorem. Yeah, but as I said, one of the key ideas is to use Soundararajan's proof rather than the original Kaczorowski-Perelli. And here again, between 1 and 2, there are no elements. So this is the. So this theorem, by the way, appears in BR20. It's on the archive. But the analog of this theorem for the extended Selberg class is probably the most difficult of the theorems of Kaczorowski and Perelli, right? We provide a completely different and much shorter proof in our much more general setting using stationary phase techniques in lieu of the refined analysis of the Fox hypergeometry function. So this is again, the starting point is Soundararajan, but we have to go somewhat further, significantly further, right? So we are able to use Soundararajan's transform, as we will see, right, to prove this theorem. So not only do we get a proof in this more general context for A sharp, right, no restrictions on the absolute convergence, abscissa of absolute convergence, no restriction on the number of poles, etc. Much more general gamma functions in the functional equation. But we also, in fact, get a considerably shorter and simpler proof. And that shorter and simpler proof, of course, works in the original setting of the extended Selberg class as well. So even in that case, I believe our proof is considerably simpler. Now, Booker also has some theorems in this direction. For his class L, again, I emphasize that's a smaller class. And in any event, Booker only goes up to 5 by 3. So he says there are no series of degree up to 5 by 3, between 1 and 5 by 3. So, okay. So I'll come back to this. I'll just state a couple of new results. What can we say for D bigger than or equal to 2? So that is somewhat new. So when D is bigger than or equal to 2, right? In general, there are no classification results. It's extremely hard, and nobody, even in S sharp, it seems to be some kind of natural barrier which is quite difficult to get over. One of the problems is that, so far, for example, the techniques, whatever I've been talking about, does not involve an Euler product. And the only way you're going to get a theorem for D equals 2 and beyond is to invoke the Euler product. There are, in fact, counterexamples in some sense. There is Marvin Knopp has shown there is no reasonable way to classify Dirichlet series if you do not have some extra arithmetic information, either an Euler product or holomorphy by twists of characters or something. Something extra is needed. You can't have just one L function and the functional equation without more information. But we do have the following omega result, right? So if Fs is in A sharp, D, for D bigger than or equal to 1, then we can prove that the abscissa of absolute convergence is greater than or equal to half plus 1 over 2. That much we can prove. So in particular, of course, when D equals 1, we know that the abscissa of absolute convergence is 1, which we know because we have a complete classification. For D equals 2, we get 3 by 4, right? And of course, in general, we get half plus 1 over 2D. Okay. Again, Katrovsky and Pirelli have an analogous result for S sharp. This is not as hard as some of their other results. But once again, I want to emphasize our proof is very different from theirs and follows the methods of BR20. That is where the case of degrees between 1 and 2 was treated. Okay. Since we impose very few conditions, so it should be on Fs, I'm sorry, our results are valid for a wide range of automorphic L functions. For instance, all those arising in the Langland-Shahidi method, including, there are some very exotic L functions associated with the exceptional groups because there are, and one knows very little about them, except that they have meromorphic continuation with a finite number of poles and a functional equation. But because we are not imposing any restriction on the absolute convergence, on the abscissa of absolute convergence, such a result will be valid in those cases also. So there are a large class, and of course, valid for L functions of modular forms of half integral weight, Siegel modular forms, etc. Okay. Of course, hello, yes, is there a question? Okay, so I think not. Okay, so these are our results. So in the remaining 8 to 9 minutes, I will. Yeah, so I'm hopeful. So, Kalsarowski and Pirelli have also investigated the phenomenon of resonance, and that's something Soundarajan, I think, introduced and studied initially, but it's been pushed for things in S sharp. And I'm hopeful that our methods, that is really, which is refinements of the stationary phase, can work in that case also, right? So this will require a somewhat more refined analysis. If you like, in some sense, this theorem 7 is a kind of zeroth order attack on that, but if one refines the method somewhat, I'm hopeful that those questions can be attacked also. Okay, so I will just very briefly maybe say what the strategy of the proof is, broad strategy. And I'll, in fact, one uses similar techniques for theorem 7 also, but I will just stick to, and for, classifying series of degree 1, but I will just give theorem 6. Theorem 6 is the case where 1 is less than D is less than 2. Okay, so basic idea is to use L2, right, estimates rather than work with either L infinity or other things which are typically used in Kalsarowski-Pirelli's arguments. So use L2. So of course, if I'm assuming that the abscissa of absolute convergence is sigma A, then there's essentially an omega result for the L2 norm, which is that it is roughly of size sigma A minus half. I mean, it's an omega result with sigma A minus half minus epsilon. Okay, so it's practically of size sigma A minus half. That's the point that we know, and that's what we'll use. And our aim is we'll get an O estimate for this L2 norm. We will show that actually it is t to the sigma a minus half minus delta by 4 for some delta greater than 0. Okay, that's the point. So this is of course incompatible with the previous omega estimate. That's the strategy. And the starting point is a transform first exploited by Soundarajan for the case d equals 1. All right. So we're doing that. Then what happens? Sorry, I'm getting a window popping up. Yeah. All right. So here is a transform. Okay. Sorry, I haven't got to the transform yet. Before that, let me just point out that the standard use of the inverse Mellin transform of the function f of half plus it plus w against gamma w by pxw allows you to replace this f half plus it by a convergent Dirichlet series, right? So essentially, standard techniques say you can write f half plus it as some convergent Dirichlet series. More to the point, essentially, this is a Dirichlet series for which, if you want to estimate its size, we really have to take terms only up to x, because once n exceeds x, we have extremely fast exponential decay. So this is a standard construction, and you'll get two error terms R1t and R2t. It'll turn out that R1t again has some kind of exponential decay, so we won't get into it. Okay, and R2t, by the way, this x should be half. There's a typo there. It's not important, but R1t is the easy thing to deal with, so I won't talk about that. There's another remainder term, that's R2t. Okay. So what is R2t? Again, I put z here. This should be half. Sorry, I worked with an arbitrary parameter first, and then I forgot to replace that by half. So this is half. So what is R2tx? It is really just this integral on a line in the left half plane minus p plus et. Okay, that's what it is. Okay. Now Soundarajan has this transform that he looked at. Okay. And what you're doing is you're integrating on an interval of rough approximate length alpha t, and you're hitting your f half plus it with this function e to the it log t by 2 pi e alpha minus I by 4. So what is the point of this particular thing? This is, well, there are several ways. One reason this is there is because when you apply Stirling's formula, this is exactly the kind of function that's going to show up. Oops. Okay. So once that happens, sorry, some interruption. Anyway, so here is a transform. So what you can do is you use a lemma, and inside the transform, you replace your f half plus it by this convergent Dirichlet series times in. Okay, I'll tell you what in is in a second, and two remainder terms. So the remainder terms are just the old remainder terms, small rit, and you hit them with your e to the it log t by alpha, right? So, and in is this interval, this integral over an interval of length alpha t, e to the it log t by 2 pi e alpha n I. So the point is to estimate this integral using stationary phase, right? And the point, the real issue is that there is a lemma. What one can do is use a lemma introduced by Bombieri and Bourgain, right? It's actually very elementary, but it nonetheless turns out to be powerful, as one might expect from a lemma introduced by Bombieri and Bourgain. And so you get this oscillatory integral. And in our context, what we will end up having is t to the oscillatory integral form t to the sigma e to the I fnt. And fnt will have this form, t log t by 2 pi e alpha n. That's the key point. What is the real point about fnt? The real point is that f triple prime t is nothing but f double prime t square. Okay, that's the key point that makes everything in these arguments work. So if you look at f double prime fn double prime t, that looks like 1 over t, and fn triple prime t looks like 1 over t square. So if I square this second derivative, I get the third derivative. That's how all of these things happen. And the net result is that when you try to evaluate these integrals ln, then you get a very precise way of evaluating it. And crucially, you get some O of alpha t. This sigma, again, I apologize, should be 0 in this case. Yeah, so there's a small typo there that should just be 0. But okay. The point is the Bombieri-Bourgain lemma gives you a saving of alpha t over the trivial estimate and of about t to the 2 by 5 over the previously available saddle point or stationary phase estimate. That is the key. You're saving a power of alpha t. I mean, you're saving a factor of alpha t. All right. So I'm running out of time, so I'll just go through. So if I just apply this, then what happens is, the transform actually becomes this summation a n e to the minus 2 pi I alpha n times some rapidly decaying term, and then I get some estimate like this, alpha to the minus half x1 to the sigma minus half plus epsilon. Roughly, I'll just tell you that x1 has roughly size t. So if you think about it, this has size t to the sigma a minus half. But the left-hand side, is t to the sigma a minus half minus epsilon for every epsilon. So what we'll do is we'll let alpha be a small power of t, and in that case, this O estimate will actually come in under the omega estimate. Okay, that's the crux of the idea. Having used Bombieri-Bourgain, we get a relatively small error term, and that's what we can do. We do the same thing for this R2 alpha t, except it's much harder to estimate it. So notice that R2 alpha t also, it's a double integral, and it carries the same oscillatory function in some sense in the integrand. There's much more work to do here. So you have to switch the order of integration, then switch the order of summation, use Bombieri-Bourgain, modified Bombieri-Bourgain for a function that looks similar to our previous FNT. Okay, and again, what you get is a saving of alpha to the d, t to the d. And you get a term of this size. And the point is, if you had used a trivial estimate, you would have got p minus eta plus 1 here. This power of alpha dt to alpha to the dt to the d would have had a plus 1 there. Okay, that's it. So I'll make two more remarks, and as I said, I'm already a minute over. The role of this parameter p is also crucial, right? When we break up this R2 alpha t, it turns out that allowing p to be large is important, because then you can make this term very small. Okay. And another important improvement over previous arguments is that we keep track of the behavior in both alpha and t. So skipping over the details, what you get is that h alpha t is this sum, yeah, which has size roughly t to the sigma a minus half minus epsilon, okay, omega estimate, and you have this smaller O estimate. And you can do exactly the same thing by evaluating h alpha t in a second way. You use the functional equation first, apply Stirling's formula, repeat analysis, and you get the same estimate for h alpha t. So the upshot is, this is the upshot. And using Parseval's formula, you just evaluate the left-hand side, right? So Parseval's formula will tell you that summation mod n square half is this, and that's the absolute. So I've rushed through this a bit, but I think the basic point is made. You will have an omega estimate, and that is bigger than your O estimate. So I will stop there. And yeah, thank you. Sorry, I went a couple of minutes over. Yeah, so I'm done, Shankar. Or maybe I have to mute. Is that an issue? Let me just try. Yeah, sorry. It seems to have muted everybody and not allowed. I think you should be able to unmute now. Can you just try?
Yes.
Yeah, okay.
Okay, thank you very much for this nice talk. I have one small remark. Regarding the oscillatory integral estimation, in the particular case, possibly due to Edmund Landau, if I'm right. This is one point.
No. The point is the error term.
Yes.
Is smaller with Bombieri-Bourgain. It's an improvement.
I see. Okay.
Over previous ones.
And another.
I don't know the history too well. Maybe Balu knows it.
Yes. And another thing I just want to ask: do you allow negative degree also?
Negative degree is not an issue. Okay. You can't really have functions of negative degree. Although I said
because in the degree conjecture you are writing that when D does not belong to Z.
Right. No, it should be Z greater than or equal to 0.
Okay, fine.
So yeah, that's
Alright.
the interesting case.
That is why
In fact, I failed to make this point adequately, and I think when I gave a talk previously, and I think Anup Dikshit pointed out I should, of course, be more careful, and I should have said that.
Thank you very much. Thank you very much for the nice talk. Any other questions, please? Remarks, comments?
Hi, can you hear me? I'm Srini.
Oh, hi. Yeah, I can't see you, but
Ravi.
yeah, I can. Yeah.
I unmuted my mic video. So, in one of the things you said, ratio of 12 functions.
Yeah.
It is having infinitely many poles, right?
One expects, yeah, right? One can.
One expects. There are some theorems by Balasubramaniam, Ramchandra, Shankar, and myself, where we have considered, ratio of translates of zeta functions. Okay, take bunch of zeta functions.
Yeah.
So product of zeta s plus alpha 1, zeta s plus alpha 2, something like that, and divided by zeta of s plus beta 1, zeta of s plus beta 2, and we show that there are infinitely many poles. Maybe that may help in this your expectation. The methods there.
No. So I have to say that, those are kind of just negative for us in the sense that, right? I mean, I know, of course, you have a bunch of other theorems also, right? Saying that there are infinitely many poles of one function, the Selberg class, which is not there and so on. No, my point is, in general, of course, one always expects, infinitely many poles, right? The zeros of kind of primitive L functions are obviously going to be very distinct. One doesn't expect them to share more than finitely many zeros, perhaps not even more than one. I don't know. So all I'm saying is, why do I allow things in the denominator? I'm saying, yeah, of course, at some level it's silly because, you're never going to actually get an example. That was my point. On the other hand, the only way to prove that such quotients have an infinite number of poles is to use some methods like this, or of course, methods that you have used previously and so on. But they're kind of all similar in spirit, in the sense that, you assume the quotient has a finite number of poles, and then you actually end up getting a contradiction, or you explicitly show that there are, by counting zeros, that there are more zeros in the denominator than the numerator or something. Or there are, of course, these techniques of Bombieri and Perelli also. I think for instance, CM elliptic curves, where there's something somewhat different. But if you want a very general method, then one has to do something like this. Specific examples, of course, one can prove much stronger the results, as you have done, I know. So
yeah, good. Okay, nice talk here, Ravi.
Yeah, thanks.
Any other questions, please? Okay, if not, let me thank the speaker, and the next speaker is
so thank you again, and happy birthday, Balu, in advance. So so I'll just transfer the I'll transfer the host.
Transfer the host. Thank you.
Right. Just give me a second. I'm trying to find you. Are you under Anup, name wise? Anup, what is your Zoom account called?
It's called Anup Dikshit. Anup Dikshit. AD.
Okay. AD. Okay. I was looking for Anup.
No, it is yeah. You can just search for a participant as
That's
Anup.
what I'm doing. I'm not able to find you. Under Anup, I don't find. There you are. Okay, good. Make host. Okay. It's done, I think. Just check.
Yes, it's done. It's done.
Okay, great. Thanks a lot. Yeah.
No worries. No.
So I'll just say stop share also.
Yes.
Okay. Welcome, Rita Pratha.
Thank you.
Okay, our next speaker is Professor Rita Pratha Munshi. Rita Pratha, could you please share the screen?
You have to first allow me. Can I do it?
Yeah,
now?
I just made you the host. You should be allowed to share.
Yeah. Let's see. Does it look good?
Okay, welcome all the participants. Now the second lecture today is by Professor Rita Pratha Munshi from Indian Statistical Institute, who will speak on some applications of delta symbol. Professor Rita Pratha.
Thank you, Shankar.
Yeah.
And let me start by thanking the organizers for the kind invitation. So it's been a wonderful conference, and I'm looking forward to participate in the other talks too. Yeah, happy birthday to Balu. I think it's on 15th, right? Day after tomorrow. But I must tell the organizers that I'm expecting a slice of cake. So you have to just send it to me by post. With that, so let me start today's talk. The topic is some applications of delta symbol. And so these are going to be some recent applications. So something that I worked out in the last 3-4 months, probably. Okay, so let's go straight to the statement of the theorems. So the first theorem I want to mention is a joint work with my student Sumit Kumar and my former postdoc Saurabh Singh. And it's about level aspects of convexity. So it's about bounding the size of L function inside the critical strip, actually at the central point, 1/2. So what we have here is we have a GL2 form F, so of level P1. You can take it to be, say, a holomorphic form for SL2Z of gamma naught P, P1. And pi is a GL3 form. So it's a Heike-Maas-Kass form of level P2. And I'm going to assume that P1 and P2 are prime, and also they're distinct, so they're co-prime to each other. So that C, which is P1 cubed and P times P2 square, is the arithmetic conductor of the Rankine-Selberg convolution of F and pi. Okay, so I'm not going to go into the definition right now, but you will see something about Rankine-Selberg L function later in this talk. So I'm going to, so the main content of the theorem is that, that the central value of the Rankine-Selberg convolution, L half F cross pi, is bounded by c to the power 1/4 minus some delta, where delta is positive, as long as my choice of the prime P2 lies between square root of P1 and P1 to the power 3/2. Okay, so C is the arithmetic conductor of the L function, and c to the power 1/4 is the convexity bound, and we are getting something subconvex as long as our choice of the levels are in certain range. Okay, so that's my first theorem, and let me make some comments about this. So first, the Rankine-Selberg convolution pi cross F is known to be an automorphic form for GL6 of level C. This is a result due to Kim and Shahidi. And so c to the power 1/4, as I said, is the trivial bound or the convexity bound for the central L value, which comes directly from the functional equation. It's not that difficult to prove. And the bound that I have written down here, I'm not explicitly writing down what delta is, but later when I give the proof of this theorem, you'll see what exactly we get as the bound. And that bound turns out to be strongest when P1 and P2 are of comparable size. So if you take two distinct primes which are not same, distinct primes which are of the same size, then the bound that we get is strongest. Okay, and also let me remark that the subconvexity problem, so the subconvexity problem for such L function is still open when one of the forms is kept fixed. So when pi is fixed and you're varying the level of F, or where F is fixed and varying the level of pi, the subconvexity problem is still open. Okay? But as long as you have a hybrid range, you can get something better than the convexity. Okay, the second statement is a joint work with Roman Polwinski and G. And it's about twists of or exponential sums involving Fourier coefficients of GL2 forms. So let's take F to be a Heike modular form or a Heike-Maas-Kass form for SL2Z. And then we look at this sum lambda fn. So this lambda fn's are the normalized Fourier coefficient of F, twisted by E of alpha into the power beta. And the length of this sum is capital N. And the trivial bound that you can get from, say, the Rankine-Selberg theory is n to the power 1 plus epsilon. And we can prove that it's bounded by n to the power 1 minus delta for some delta positive, as long as beta is less than 1.6381 dot dot dot. Okay, the precise value of this number over here has to be still is under consideration, but it looks like something like this is achievable by the method we are applying. Okay, so let me comment that it was known for beta less than 3/2 or beta less than 1.5. It was known due to work of Utila long back from 1980s, I guess. And it was recently extended, and the same bound range was proved by Agarwal, Holwinski, Lean, and Key using a different technique, using delta method actually. And this actually corresponds to the Weil threshold. That means if you use the Weil bound or the methods that gives you the Weil bound, then you get non-trivial bound for such sums for beta less than 1.5. Okay? And let's recall that the Weil bound for in this case was proved by Anton Gode in 1980 or 81, and the bound is that this L function for this modular form or Hecke mass class form is t to the power 1/3 plus epsilon. Okay? T to the power 1/2 is the trivial bound or the convexity bound. T to the power 1/3 is the Weil bound. Okay. So in that sense, this range it gives you extends the range to something sub-Weil. Okay. So going beyond beta 1.5 is sub-Weil in this problem. So it's something about sub-Weil in GL2. But our main target is to really extend the range beyond 2, and it seems to be a very difficult problem. And the main motivation is it's related to the analog of Dirichlet divisor problem for class forms. All right. Okay, so the last theorem that I want to mention is still work in progress, very much in progress. Actually, we just started working on it, but we have a sketch in place, and this is something that we are expecting to get. So suppose pi is an SL3Z Hecke mass class form, and then we're looking at the second moment of L half plus IT pi. Okay, and so there's the integral which runs from t minus m to t plus m. So the integral is in a short range. It's not the full moment. And we are expecting to get something like t to the power 3/2 minus twice delta, as long as with delta positive, as long as m is between t to the power 3/8 and t to the power 5/8. So as you know that the second moment of GL3 functions is still a big important open problem, and we don't even know for it corresponds to the sixth moment of Riemann Zeta function for which our result is not that good, right? So we don't really expect to get very good results here, but there will be applications of that. So let me recall that Xiaoqing in her famous work had this integral. So it was a consequence of the spectral bound that she had in her paper is the moment for the symmetric square L function. So you're looking for any SL3Z form. She looked at the symmetric square of a GL SL2Z form, ranging from the t minus t to the power 3/8 to t to the power t plus t to the power 3/8, and she bounded it by t to the power 3/2 minus 1/8. So for her, the delta was 1/16. And using such a bound, one can derive a bound for the L function in the t aspect, like Xiaoqing had for the symmetric square L function, the t aspect. She had 3/4 minus 1/16. So 3/4 is the trivial bound, and so she had a saving of 1/16 over that. As consequence of our result over here will be like we'll have a bound of t to the power 3/4 minus delta. So it will be a bound in the t aspect for SL3Z form, which is coming from the moment computation. Okay, so previously, directly applying the delta method, I had proved that the bound 3/4 minus 1/16 for any SL3Z form, and the method was extended and sharpened by Keshav Agarwal, and he got 3/4 minus 3/40, which looks somewhat like the limit of the delta symbol approach if you do it directly. But if you mix this thing up with the moment method, then you can get something better. And if I'm allowed, I can say that if it looks like the optimal choice for m over here is square root of t, and in that case, delta turns out to be 1/8. So the subconvexity bound that we were expecting is 3/4 minus 1/8. So it will be like it will be like the saving will be like the double of the saving that I had previously. Okay, so these are the three theorems that I wanted to mention. So yeah, so all of this will be related to what's called an arithmetic correlation. So we'll see that all the three statements ultimately boil down to showing that certain arithmetic correlation is small. Right? So what do you mean by that? So we start with two sequences, AN and BN. So they will be finitely supported. And we want to look at the sum S, which is the sum of AN times BN. And so we'll have some standard properties for these sequences. For example, we will be assuming that that they are supported in some dyadic range, and in the L2 sense, at least that the individual terms will be bounded by n to the power epsilon, so that the L2 norm will be average, will be 1 in average, okay, or n to the power epsilon average, and we'll assume that at least one of them is oscillating. Okay, so like sum of AN or sum of BN is small. If both are not oscillating, then of course we do not expect any cancellation in the sum. Okay, and then the standard definition of correlation is this, and the correlation is then can be written as S by N plus big O of n to the power minus delta. So if you show that S is smaller than N, better if you get a better bound than the trivial bound, then we'll be showing that the correlation is smaller. So that, than the trivial one. Okay. So in fact, we'll be saying that these two arithmetic sequences are independent if you can bound this S by some power into the power 1 minus delta for some delta positive. All right, and so the general recipe that we'll be using is our delta symbol approach. Okay, so let's try to explain what the idea is. So we'll be looking at the space of all functions which are supported between in this dyadic range between n and twice n, supported on the integers, and taking value in the complex numbers. So this gives me a vector space of roughly of dimension n. And if you have two arithmetic sequences, that's the same thing as saying two vectors in this space, then the sum or the correlation sum that we are looking at is actually an inner product of A and B bar, right? And so we can have a spectral decomposition of this inner product. So if you have an orthonormal basis of the space, then this inner product can be written in this manner. And then, so this will be our starting point. So start with an orthonormal basis of the space and write in this manner. And then for this individual inner product A and psi V, so this inner product of the sequence A with the basis vector psi V, we'll have some sort of a summation formula to transform this sum to something else. And the type of things that we have in mind is Poisson summation formula, or like Voronoi summation formula for GL2, GL3, or higher rank Voronoi summation formula. And we'll be doing the same thing with the other inner product, also psi V B bar. And so with that, S will be transformed into something like this. So here, these are the dual coefficients. This is the dual sequence A star and B dagger. And once we have dualized, then the next step will be to apply Cauchy to get rid of one of the sequence. So here I'm getting rid of the A star n. So here we'll be using the fact that it's the L2 norm is 1 on average, right? And so, and after that, we'll just open the absolute value and try to execute the sum over n it using some summation formula. So usually, depending on what type of vectors you're allowing in the orthonormal basis. Okay, so these are the basic steps. So there are two summations. So start with a choice of basis, and the choice of basis will depend upon the problem that you're looking at. And then you apply summation formulas, and then you apply Cauchy and open the absolute value square and apply another summation formula. So these are the basic steps. And finally, the end game, sometimes it will be required, is to see what else can be done. Okay, so this is something completely vague, but usually you'll see that there's something else that can be done at the end. Okay. Okay, so now how do you get the orthonormal basis? So we are looking for vectors like this, which satisfy this. So delta VW is a Kronecker symbol, which is 1 if V equals to W and 0 otherwise. Okay, so that's same thing as trying to get an expansion of the usual Kronecker symbol. So here V and W are vectors. Here N and M are integers. So this is the usual expansion of the Kronecker delta symbol. Okay, so this is the type of formula that we're looking at. And once we have such an expansion, we can surely write S as this. Okay. And so the problem now is to see how to get expansion of the Kronecker delta symbol and what type of functions can you get over here to get such an expansion. Okay, and one source of such an expansion is called the circle method or the delta method. And in this talk, we'll just restrict to this usual circle method and delta method and not talk about higher rank analogs of this. Okay, so what is the usual circle method or delta method? So, roughly speaking, it gives you an expansion of delta nm, which looks like this. So here, E of this is E of x is e to the power 2 pi I x, which is standard notation. So we are taking integers q going roughly up to square root of n. So recall that our sequences were supported in between n and twice n. So the length of the equation is n equals to m. The length of this equation was n, and we are allowing modulus going up to square root of n. So that's the usual thing that we do in circle method. And then we have a sum over a modulo q, a co-prime with q. The star denotes that. And we have this. So this is a very rough version of what we mean by a circle method, or in terms of trigonometric functions. So if we had, from here we can write down the vector psi vn. So v is going to be the pair a and q. So a is going to be modulo q co-prime with q, and q is any integer going up to square root of n. And psi of a q n is going to be 1 by square root of n e of a n by q. Okay. So that gives you an expansion of delta nm. Of course, as I said, that this is an oversimplification because we never have such a clean formula for delta nm. So there is always some intricacies hiding somewhere. And here is this is the right version of Diophil and the Ivanich delta method. They have a function h, which you can write down explicitly, but it's not really important to know what h is explicitly. As long as you know the properties of h, you can work out the details. Okay, and in this form, you can actually you have the choice of q. You can pick any q to be any integer. But if you want to kill the oscillation in this h function, then you take q to be like square root of n. Then at least in the generic situation where small q is like capital Q, this h has no oscillation whatsoever. Okay, so this is another version of the circle method. This is due to Klosterman. And here, the h part, you'll see that there are some difference that here a was a full sum modulo q. The a was not actually involved in h. In the Klosterman version, the a is involved in h. So this part is the h part, the analytic part of the circle method. This is the arithmetic part. Okay, but it's kind of explicit. Okay, it's completely explicit. This is the trivial delta method. Surely, if you take your modulus to be much larger than the size of the equation, then this already is good enough to detect the event n equals to m. Okay. And you will wonder why this will be of any importance here. But this has been recently used in this field in the delta symbol approach to get very non-trivial bounds. So it's it's kind of counterintuitive. Okay, so usually when you do circle method, you really want to make the modulus as small as possible, but I don't know why it works, but sometimes even the trivial delta method gives you something non-trivial. Okay, another delta methed is it's called a Bessel delta method. It's due to Keshav and Roman and Lin and Jiki, and it looks like this. It's a kind of a mixture of the trivial delta, but you also have, so you not only have an arithmetic part. So here you can take q smaller than the size of the equation. You have to push in some oscillatory integral here, which involves the Bessel function. Okay, so the point here is that already if you just stick to trigonometric functions only or Bessel functions, then you have different versions of the circle method and the delta method already played. Okay, so as I said that the choice of the delta method, what type of delta method you'll be using will depend upon the problem that you have in your hand. Okay, and so you have to be a little choosy. That is, pick the right method. Usually, if you pick the wrong method, you get something worse than the trivial. So you know how to get to the right method. Okay, so this is the proof of the first theorem. So the first theorem was about the Rankin-Selberg convolution of GL3 and GL2, and it's in the level aspect. So let's recall what the F was. So F is going to be a GL2 form of level P1. So if you are more comfortable, you can just take F to be a modular form of level P1, say trivial Niventy plus fixed weight. Okay. And pi is a GL3 Heckler-Mass class form of level P2. Then the Rankin-Selberg convolution of this pi and F is given by this Dirichlet series. So lambda Fn, these are the normalized Fourier coefficient of the GL2 form F. Lambda pi nr are the normalized Fourier coefficients of the GL3 form pi. Okay, and so we have nr squared to the power s in the denominator. And these things can be shown to be converging absolutely for real s greater than 1. And since we are picking f and pi to be Hecker forms, you also have a Euler product representation of this L function in this half plane. And that Euler product will have 6 factors. For each prime, there will be 6 factors because it's a GL6 form, really. And you can show that this extends to an entire function, and it satisfies a Riemann type functional equation. That means it takes s to 1 minus s. So the center of symmetry is 1/2. The arithmetic conductor of this L function is P1 cubed P2 square. So you take the P1, if it's twisted by GL3, so you take P1 cubed. And P2 pi is twisted by GL2, so P2 square. Okay, so that is of course, we are assuming that P1 and P2 are co-prime. Okay, and also, I think I mentioned in the first slide that it's known that this actually corresponds to an L function automorphic form on GL6. Yes, it's an L function of an automorphic form on GL6. Okay, and so we have a functional equation, and a consequence of that functional equation is this bound. Okay, so our problem was to get a bound for the central value of this GL6 L function, and from the functional equation we derive this. Okay, so this is so c to the power 1/4 is the trivial bound, and we're trying to beat it. So we have to allow a delta positive, and in that case, I have to take my n here between square root of c, which is the square root of the conductor. That's the length of the sum appearing in the approximate functional equation. And so since I'm on minus delta over here, I have to go down up to c to the power 1/2 minus 2 delta. Okay, so this is the bits and pieces of the expression that appears in the approximate functional equation of this L function. Okay, and so we take this. So this is where the main problem is. So this is like the arithmetic correlation that I mentioned of the GL2 Fourier coefficient LFN, lambda Fn, and the GL3 Fourier coefficient lambda pi n1. Okay, so usually you'll have an R over here, and R will also be ranging in some short range, but I'm going to ignore that part. I'm just going to take R equals to 1. Okay. All right, and so if you take the trivial bound for Sn will for this sum, you apply Cauchy and you use the Rankin-Selberg theory for GL2 and GL3, then you get that Sn is bounded by n to the power 1 plus epsilon. And if you put n to the power 1 plus epsilon over here, then it becomes square root of n, and n goes up to square root of c, so it will be square root of c, so it's c to the power 1/4 plus epsilon, and that will be the convexity bound. Okay, so the trivial bound for Sn gives you the convexity. To get a subconvex bound, you have to showed some cancellation in the sum Sn. That is the same thing as showing that these two Fourier coefficients, sequence of Fourier coefficients, are independent. Okay. Okay, so as I said, we follow the recipe. We apply the delta symbol. So we separate the oscillation of the GL2 Fourier coefficient from that of the GL3 Fourier coefficient, delta NM. And then we use an expansion for delta NM. And here I'm going to use the Duke-Filnander-Ivanich delta method. So that will introduce these trigonometric functions. And then there was an a slightly complicated function over here. And as I said, that if I take Q to be like square root of the length of the equation, then that H function is not really oscillating, at least in the generic situation. And so I'm going to ignore that from the sketch. Okay, so in practice, you have to take look for you have to consider smaller values for small q also, and in that case, that part will be oscillating, and so there is some complications there, but it can be worked out. All right, so this is the expression for Sn. So after using the expansion for delta Nm, and if you bound this here trivially, then you'll see that the bound is n squared. Okay, so by sacrificing the equation, we have lost the size of the equation n. So our problem now will be to gain back that n, capital N, and something extra. Okay, and I recall the second step was to, okay, so this is the individual inner products here. And now we want to apply the summation formula to this and this. In this case, those are readily available. Those are called the Voronoi summation formula. So first, for the GL2, if we apply the GL2 Voronoi summation formula, this is the expression that you get. So A becomes A bar because the level is P1. You get a P1 bar over here. And this will be the length of the dual sum. Okay, this is Q square. So Q is the modulus here times the level P1 divided by the initial length. And if you recall the size, as Q was taken to be square root of N, so the dual length is P1. Okay, so I'm ignoring the factors. I'm not writing that this is equal to this. So there will be some factors appearing over here. There will be a Henkel transform over here and all that. And I'm going to ignore because I'm ignoring the oscillation in the weight function. And so the Henkel transform is just a kind of flat function over there. Okay, so next we apply the GL3 Voronoi summation formula to the other sum. And here in this case, this additive character gets transformed into the Klosterman sum. So this S here is the Klosterman sum modulo Q with these two parameters. And the dual length is, again, so it will be the cube of the modulus here. So that's Q cube times the level of the form pi P2 divided by the initial length N. And this turns out to be P2 square root of N, okay? Because Q cube was n to the power 3 by 2. Okay, so we get this as a two dual lengths. And now we look at the A sum. Okay, so we have the sum over A modulo Q of this Klosterman sum written over here. And from the GL2 Voronoi, we are getting these additive characters over here. And the nice feature of this GL3 cross GL2 thing is, in fact, it's true for any GLN cross GLN minus 1, is that this character sum after these two Voronoi summation formulas will just reduce to something like this, which is just an additive character. So it's E of P1, P2 bar, M, N bar by Q. And if you see how this depends on M, you'll see that it's like a geometric series. So it's like something to the power M. So some point on the circle to the power M. So as you vary M, it's just going around the circle in a geometric fashion. Okay, so after all this transformation, this is the expression that we end up with. So Q is like root n. This is the dual length for the GL3. This is the dual length for GL2. And this is what happened to the basis vectors, actually. So these were coming from the basis vectors. And after all this transformation, this is, oh, I should have an E over here. Okay, it's E of P1, P2 bar, M, N bar by Q. All right. Now, let's see how much we have saved by this. So we have applied a GL2 and a GL3 Voronoi. So here from the GL2, so the saving here is square root of n by square root of P1. The saving here is square root of n by square root of P2 square root of n. And the saving here is square root of Q. Okay, so that's the three things that we have said. So this is the saving from GL2 Voronoi. This is the saving from the GL3 Voronoi. and n to the power 1/4, which is square root of n, is the saving from the a sum or the character sum, and this turns out to be n by square root of p1, p2. Okay, and recall that we had lost capital N, and our problem was to gain back capital N and something extra, and so here we still need to save square root of p1, p2, and something extra. Okay. All right. So the last step was, as mentioned, we apply Cauchy. So we bring the GL3 term outside. So we are getting rid of the GL3 Fourier coefficient. We still have the GL2 Fourier coefficient inside, but here, okay, again we have the E over here that's missing, and it's the reason we put the GL3 outside is that this part is very nice with respect to GL3. It's just a geometric series. So when we open the absolute value square and bring the M sum inside, it will just be a geometric series, which we know how to add. Okay. Okay, and now since we have done Cauchy, our job is to save P1, P2. Okay, before Cauchy, it was square root of P1, P2. So it gets squared. And so you have to save P1, P2 and something extra. And again, so we open the absolute value square. So these are the terms coming from the whatever we had inside, absolute value. And again, sorry, there should be an E over here, okay? So E of this, okay, so this is a geometric series. And now if we apply the M sum, you can actually apply Poisson summation if you want. Okay, so the amount that you save is, you save the whole length of summation. That's the whole length of summation of P2 square root of n. In the generic situation, and generics means that the terms there is not too close, right? So, and the length gives you a sufficient saving if the length is larger than P1, P2, that's how much we need to save. So that happens if P2 is greater than square root of P1. So this is one part of the theorem, because we need, recall that P2 had to be between square root of P1 and P1 to the power 3/2. So this is one part. So we say that the saving in the generic case, which is the off-diagonal case, is fine if my parameter P2 is larger than square root of P1. And now if you look at the diagonal case, so the diagonal case is when here we do not have much oscillation, where the terms are near each other, right? And the extreme situation is when N1 equals to N2 and Q1 equals to Q2. And in this case, we save nothing in the M sum, right? Because then this is just identically 0, and E of that 0 is 1. So there's nothing to save over here. But we save the diagonal. So the saving will be the number of N2 times the number of Q2. So that's P1 times square root of N. And that is enough. That's larger than P1, P2. If P1 to the power 3/2 is larger than P2. Okay, so we get this range. And now if you follow the argument here, then you'll see that the ultimate bound that you get for the L function is conductor to the power 1/4 plus epsilon times this term. So one of this term is coming from the off-diagonal contribution. The other term is coming from the diagonal contribution. And so we want this to be smaller than 1 by n to the power delta. And that happens if P2 is larger than square root of P1 times n to the power something, and P1 to the power 3/2 is larger than P2 times some n to the power something. Okay, so that gives you the level aspects of convexity for GL6 L function. All right, so now we turn to the other problem, the second theorem, and recall that it was about the sum S. So we have the Fourier coefficient. So F is a fixed SL to Z cusp form, okay, and which has normalized Fourier coefficients. So lambda Fn's are the normalized Fourier coefficients. And for simplicity, I'll just write it to be lambda n. Okay, so you have lambda n e to the power n e of n to the power beta. I'm ignoring alpha. You can put an alpha over here if you want. So I'm just looking at the simple sum lambda n e n to the power beta. And the length of the sum is capital N. And I want to see whether we can have a power saving over here. And for what values of beta is such a power saving allowed. Okay. So again, we use the delta symbol to separate n from m, the oscillation of the Fourier coefficient, and e of m to the power beta. And now, so in the sketch, I'm going to use the Klosterman version of the circle method. In the paper with Roman and G, we use the Bessel delta method that they had already used in their previous paper, okay, because that gives you something. Technically, it makes things simpler. Okay, Klosterman, and if you follow Klosterman circle method, also you get something non-trivial, namely for some range beta greater than 3/2, but you have some technical difficulties to take care of. Okay, so but here I will ignore the technical difficulties and I'll just assume that I'm using the Klosterman circle method, okay, which we recall is given by this. Okay, and if you plug in this, so this is actually delta n is 0 or 1. That's what it's detecting, and this is n equals to m or n minus m equals to 0 or 1. So we plug in the Klosterman version of circle method here in that sum over there, and this is the sum we end up with, expression we end up with. And now we'll be using, for this one, we'll be using a Poisson summation formula because this is all GL1 type of harmonics. And here we have a GL2 Fourier coefficient. So here we'll be applying the GL2 Voronoi summation formula. Okay, so these are the next two steps. So if you apply the Poisson summation formula from here, so since this is the arithmetic part will reduce to some congruence. So you get m is congruent to a bar modulo q. Okay, and this e of m to the power beta, and this will be put in the Fourier transform, and so it's hidden over here. So there is some Fourier transform here, which involves certain oscillatory terms, which you can try to evaluate using stationary phase if you want. Okay, and so here my k is n by q squared. Okay, so so my q here will not be, so we'll choose q to be optimally at the end, and q is not going to be square root of n. In the previous case, q was taken to be square root of n from the start because the problem was in the level aspect. There was no analytic oscillation as such. This is a more analytic problem. Okay, there is analytic oscillation, and so we'll choose a delta method where there is some analytic oscillation present already. Okay, so we'll take, so k is the amplitude of the analytic oscillation present in the circle method or the Klosterman circle method that you're applying, and k is taken to be n by q squared. Okay. All right, so, and we also apply the GL2 Voronoi summation formula to the n sum, and that transforms this to this. So again, a bar becomes minus a by nq. And here we have an Henkel transform of this analytic function here. Okay, and okay, so far we have saved this much. Okay, so this is how much you save from the Poisson, and so here in the Voronoi you save square root of n by square root of k. In Poisson, this is how much you save. There is a congruence modulo q, so you have to take care of this. So that this gives you the how much you have saved from the Poisson and Voronoi, and the integral that you have. There's an integral over x over here. Yeah, this integral 0, 1. This is oscillatory, so we'll have a square root of saving in that too. So for that, you need to do some stationary phase analysis. Okay, so in total, this is the amount you save. So it's 10 to the power 3 by 2 minus beta by 2. Recall that amount that you need to save is more than n, because n is how much you lost when you choose to drop the equation. And here, this is larger than n if beta is less than 1. Okay, and beta is less than 1 is like the trivial range of the convexity range. It's quite easy to prove. And so after Cauchy, the range that we get is just the convexity range before Cauchy. And now we want to go beyond this range. So we apply Cauchy and we get rid of the GL2 Fourier coefficient. So the lambda n's are all gone. Okay, so we put the q and m part inside. And again, since the problem here is like a GL2 plus GL1, with respect to n, it's just a geometric series over here. Okay? And here we have some oscillatory factor, which comes from the Henkel transform and the Fourier transform and the X integral. I'm not going to write down explicitly what it is over here. Okay, and again, we open the absolute value square and apply Poisson on the n sum. Okay, and again, as before, we have to see whether the diagonal contribution is good and the off-diagonal contribution is good. So here, if you look at the diagonal, so you count the number of harmonics that you have inside the absolute value square. So that's the number of q and m, and that turns out to be n to the power beta by k. Okay? And in the off-diagonal, so that's how much you save in the diagonal. And in the off-diagonal, since if you look at the n sum, and since you have a geometric series, so the saving will be n by square root of the analytic oscillation. The analytic oscillation here has amplitude q, amplitude k, sorry. And so the saving will be k by square root of k. Okay, so that's how much you save in the off diagonal. Okay, so you have to get the second derivative bound for the integral transform. So you can, take the n sum inside, do Poisson, and look at the Fourier transform of this function, and just use the second derivative bound for that. That gives you a saving of k to the power 1/2. Okay, now you equate this two. So this is how much you save in the diagonal. This is how much you save in off diagonal. If you equate this two, that gives you the optimal choice for k, and see it's n to the power twice beta by 3. So it is not 1. Okay, so the q equals to square root of n is not the optimal choice in this application of the circle method, the delta method. Okay, so if you pick k to be this optimally, then here you have saved square root of k. So if you go back, you have saved k to the power 1/4, because this is how much you saved after Cauchy. So if you put that here, so multiply this with k to the power 1/4, and that turns out to be this, or n to the power 3 by 2 minus beta by 3. And you'll see that this is larger than n if beta is less than 3 by 2. So that was the range that's already there in the literature, and this is the Weil range, which corresponds to the Weil bound. And the problem, as I said, that after this Cauchy and Poisson, you see what else can be done. Okay, so with this, we hit the Weil bound, and we want to get past the Weil bound. We want to get something sub-Weil. So we see what else is there to be done at this point. Okay, so so let's go back one step. So this is the expression that you get after application of Poisson. Okay, so these are the sums, and that comes from inside. Okay, so this q and m. So we get two copies, q1, q2, m1, m2. And this is the part which you get after Poisson. Okay, so from this part, you get an equation, congruence, sorry. And here we have the Fourier transform of that analytic function that you have over here, okay, which is not explicitly written down here, right? So, and then you notice, so what we notice here is that, so everything here in this arithmetic part, everything is modulo q1, q2. And so n is too small, n is of size q square, so n modulo q1, q2 is nothing left over there. But if you look at m1 and m2, the mi's are of size n to the power beta minus half by square root of k. And this turns out to be larger than the modulus. So here m1 is modulo q1, right, because it's multiplied by q2. So m1 bar q2 is congruent to n modulo q1. But since m1 is larger than the size of the modulus, I can write it down in terms of the congruence classes. So I can write down mi as some congruence class modulo qi plus qi ri, and then still in ri we'll have something, some size left. Okay, so ri will be of size n to the power beta minus 1. And since beta is at least near 3 by 2 or even larger, we have some size in ri left. Okay, and then we consider the sum over ri. Okay. All right, and that gives you something better than 3 by 2 or something sub-Weil. So that's the idea. And now let's see what type of exponential sum. So here, if you look at the sum over here, it will be a purely exponential sum. And it's quite interesting. So let me just briefly recall what type of exponential sum. So we have, what type of bounds we have for the usual exponential sum. So in the usual problem in exponential sum is to get a non-trivial bound for sums of this type. So this is a one variable exponential sum. There's only one variable n. Okay, and you assume that this function f and the phase function over here satisfies this. So you have some condition on the amplitude and the higher derivatives of f. And the basis of these parameters a and n, you can write down a bound for s, which is a to the power k n to the power l. And then this kl is called an exponent pair. That's the definition of an exponent pair. And then you try to find out what are the possible choices are there for k and l. Of course, what you really want to do get at the end is k equals to 0, l equals to 1/2. That would be the ideal thing to get at the end. But that's not known for general type of phase function. But we still know something about the collection of this exponent pair. First, we know that 0, 1 that is a trivial exponent pair that's always there. And then the collection of all exponent pairs form a convex set. Okay. And there are two processes. One is called the A process. The other one is called the B process. So the A process comes from the Weil-van der Corput inequality. And it says that if KL is an exponent pair, then this guy is also an exponent pair. And the B process depends upon a type of Poisson summation formula with stationary phase. And it says that if KL is an exponent pair, then L minus half and K plus half is also an exponent pair. Okay, and so using these two processes, even starting with the trivial exponent pair, you can get very non-trivial exponent pairs like this. Okay, the one bad thing about this is B is involutory. So if you take B squared, then it becomes identity. So you cannot apply B consecutively. But if A is not involutory, you can apply A repeatedly in one place and still get something new. Okay, and so one nice advantage of this theory is that one can get cancellation in very short sum, okay? And that's a beautiful thing. Is that yeah, because it comes handy if you're lucky at the end game. Okay, so when you have nothing else to do, if you're lucky, you can just left with an exponential sum, and then you just use exponent pair. Okay, so that's what happened in the case we were considering with Riemann and G. So this is precisely the phase function that you have there. Okay, so we have something like this. So there are two variables, R1 and R2. Let me just go back. Yeah. So this, I wrote down the exponential sum here for only one, but I have two of them because M1 and M2 are there. So I get a R1 and R2. Okay, and the phase function here looks like this. Okay, so there's a difference of two phases, psi R1 minus psi R2, plus phase which involves both R1 and R2. Okay, and the nice feature is that this psi has amplitude n to the power beta, whereas rho has the amplitude n. Okay, and beta is like 3/2 or even larger. So the amplitude of the psi function is much larger than the amplitude of the phase which mixes R1 and R2. But nevertheless, it kind of this mixing kind of creates some problem, and so this is something we call an almost separable double exponential sum. If we didn't have this rho, then we'll surely get a very nice bound for the sum we're looking at, and a very nice range for beta. Like beta will be going up to 1.76 or something if we didn't have a rho there. But we have a rho, and that creates some trouble. Okay, and for such type of phase function, there is not much in the literature, because in the literature, if you look at the double exponential sum, the bounds that are written down are only for monomial phase function, or at least for phase functions where there is a monomial which dominates the rest of the phase, okay, which is not the case over here. Okay. So the choice is we either ignore one of the sums. So suppose you ignore R2 and we just look at the R1 sum, and then we just use exponent pair for one sum R1. Then we get some non-trivial bound. And in our case, we'll get that beta can be taken to be less than 1.56 ... So it beats 1.5. So it's a sub-Weil bound. Or we can try to develop a theory of almost separable double exponential sum. And that's what we do. And we are just still, looking at the details and saying whether it's all correct. So there is something we're developing here for exponential sums of this type. And that gives us a range which is much superior to the range that we have over here. So it gets better to be less than 1.6381 dot dot dot. So we use Bovmeri-Vanich theory over here, and that gives us the second theorem. Okay, so in the last few minutes that I have, which is just 1 minute, I'll just give you a trailer for the theorem 3. Okay, so here, recall we are trying to get a bound for the second moment, and a short moment from m is a fractional power of t. Okay, and this boils down to a shifted convolution sum problem with GL3 Fourier coefficient, because pi is a GL3 form, and there will be an oscillatory function over here. Okay, and this is the oscillatory function that plays a crucial role in the approach that we have. And you'll see that if we take m to be like of size t, so if you're really genuinely looking at the second moment of GL3, then this part is not there, and you're basically left with the shifted convolution sum problem, which is not that good. Okay, which is not, we don't know how to get a non-trivial bound for that. But if we allow a shorter range in the moment, we get an oscillatory term over here, and this is the this term we use to lower the conductor in the delta method approach that we use. Okay, and with that we get a non-trivial bound for this as long as m is between t to the power 3/8 and 5/8. Okay, and I'll not give much details about this, any more details about this, and maybe next time I'll come up with more details. Okay, so with that, thank you.
Okay, thank you very much, Rita Brata, for a nice talk. I think there are two-dimensional exponent pairs available, I believe.
Srinivasan, yeah, from Srinivasan we got something, but it is not as good as this.
Okay. I mean, I just wanted to point out there is something available.
Yeah, so he has a different A process, but that doesn't give something this strong. Okay. Slightly weaker.
Okay. Any other questions, please? Remarks, comments? Okay, if not, let me thank the speakers, Ravi Raghunathan and Rita Pratap Munshi, for the nice talks. And the second session will start at 4:30, I believe, right? Yeah, 4:30. Thank you very much.
Okay, thank you.
Okay, there is some question, it seems.
There is a question.
Akash.
Yes, in the chat, I think.
Sparlinsky. Igor has been written something in chat. We have written something.
Yeah, why do we need a lower bound on m?
I think it was about slide 4.
Oh yeah, you mean yeah, actually. Recall, I think that the delta depends upon the range of m. So if m is smaller, the delta becomes 0 at some time.
Yeah. So this was just an integral of the square of the L function.
Yeah.
Over a short interval.
Oh yeah. So you mean? Let me just go back. Yeah. So yeah, it's monotonic. That's what it's saying.
So it's monotonic with them, right?
Yeah, it's monotonic. So so whatever bound you have for 5/8 will work for 3/8. That's what you're saying.
Yes, exactly.
Yeah, that's right. Yeah, but the delta actually is quite weird, and it becomes best when t is 1/2. So the bound, so up to 1/2 you get a very strong bound, and then from 1/2 it becomes worse. Yeah, so I should probably write here from t to the power 1/2 to t to the power 5/8. with delta depending on
Okay.
on M. Yeah, thank you.
Any other questions, please? Okay, if not, let me thank all the speakers, and the next session will start at 4:30. Thank you very
I
much.
have some other question here. I don't know. As from Binay.
Yeah, Binay has.
Few words
Vinay?
about how.
Okay, Vinay has something.
Few words about how cancellation for sums of the type can be used to obtain wild strengths of convexity bounds for. Yeah, so instead of m to the power beta, you'll have t log n, right? Yeah, there. Yeah, but the method that you use also works for those type of oscillatory functions. Okay.
Any other questions, please? Okay, if not, let me thank the speakers. Bye-bye.
Thank you. Thank you.
Thank you, everyone, and special thank to the chair of this session, Professor Shankanarayan, and the speakers of this first session. Thank you.
Thank you.
And we'll have the link of the second session, different link, and please log into the other link if you want to attend the lectures there. And Ritabrata will send you the cake in December.
Okay, good.